Alright, hell yeah. So we have physics for scientists and engineers. And this is the second problem in the book, you know what I mean? And we're going to do the quick answer. It wants to know what's the density of the Earth. And I think a cool way to do it is like, hey, what are they asking? Density. And then the units are the equation. So if we know that density is like, hey, kilograms per meters cubed, you know what I mean? And maybe you don't know that. Maybe you actually know that density is just like mass divided by volume. So sweet. And typically we like to use kilograms for how much things weigh, and then meters is always a good one. So like meters cubed, even though a cubic meter is quite big, and that's where you could probably use centimeters. And so let's take a look at, and then what is like water has a density of 1. We've all heard that, but 1 what? Water has a density of 1 gram per centimeter cubed. Or it could be 1 gram per milliliter. You know what I mean? And that's also a volume. Okay, so hell yeah. So if we know that, and this problem says, hey, look up in the back of the book what you need to know. So Earth has a mass of, this is a good one to memorize, 6 times 10 to the 24. If you can memorize that, cool. And I think it's pretty easy to memorize 5.98. It's just a couple, little 2 digits less. The diameter of the Earth, just roughly, is 6 million meters. So that gets you pretty close. 6 times 10 to the 6. But if you can memorize 6.37, I don't know, it's kind of a cool one to memorize. Anyway, and so those are the ones that we're going to be using. Now, we need to know the volume of the Earth. Earth's a sphere, so we need to know that the volume of a sphere is 4/3 pi r cubed. And so, and then we just throw in the radius. So we're going to have the density is the mass divided by the volume. We're going to have that 5.98 times 10 to the 24 kilograms divided by the volume of the Earth as a sphere. 4 divided by 3 pi times the radius cubed. Cool. And if you just throw this into your calculator, you're going to get a number that maybe you're not familiar with. It's 5,523 kilograms per meter cubed. Well, so we also need to know that water is 1,000 kilograms per meter cubed. Now this is also the definition of a metric ton. You might know that 1 kilogram is 2.2 pounds. So this is going to be 1,000 times that. So a metric ton is 2,200 pounds. And I think that is a pretty cool one to know, that we all know that this is a metric ton. I don't know if I said that, but yeah, that's a metric ton. Where a ton, 2,000 pounds, a metric ton, another 200. And that's because of that. So if we take this number that's 5,000, we have to divide by 1,000 to get 5.52 grams per centimeters cubed. Now, let's go through the factor label method and figure out how to do that just all in one go. So we're going to have, this is going to be the Earth in kilograms, but we want to convert it to grams. You know what I mean? We want our answer to have grams and centimeters cubed. Cool. So what we do is you make something that's equivalent. You can say that 1 gram is 1,000. 1 kilogram is 1,000 grams. Now, this is kind of what you want to do in your head, but I wouldn't even write it like this. I would just stack them, you know what I mean? So you would write 1,000 grams divided by 1 kilogram. And know that this is kind of the useful conversion factor, and you can flip it upside down too and say that 1 kilogram is 1,000 grams. And now you're going to put it next to the thing that you're trying to change, and you need to cancel out the units. So this kilogram must be downstairs. You can't write it like this, because then the kilograms would square. Cool. So you cross out the kilograms, and now you have to multiply this number by 1,000, but now you're just left with that units in grams. Cool. And this problem's a little bit tricky because now we're going to do a factor label method with something that's cubed. And I should be slowing down, but hell yeah, we're going to kind of go through this a little bit faster. So we have volume of a sphere, 4/3 pi. We have the radius. We're going to cube it. This is going to give us meters cubed. I think we see that, but we want to convert to centimeters cubed. So the first thing I do is just like, hey, let's not worry about the cubes right now. How would I convert meters to centimeters? Well, I would say that 100 centimeters is 1 meter. I would put the meters downstairs. Meters can cancel. And cool. If I just had meters and converted to centimeters, I would just multiply this by 100. And that's how many centimeters I would have. Okay, hell yeah. So now what do we do when we have meters cubed? Well, just take your conversion factor and then cube it yourself. And then in the long version, we kind of go over this again. You can cube the 100. You can basically bring this cube inside to all these things. So if you do that, you have 100 cubed, centimeters cubed, 1 cubed, that's just 1, and then meters cubed. So this meters cubed is going to cancel that meters cubed, and now you're going to have centimeters cubed, that's what we want, and now we have this 100 cubed. 100 cubed is the same thing as 10 to the 2 cubed, which is the same thing as 10 to the exponent of 2 times 3, which is 10 to the 6. So up here, this was 10 to the 3. Down here, this is multiplying by 10 to the 6. Cool. So I think that covers it. You know what I mean? 10 to the 3 divided by 10 to the 6. Ultimately, you're just going to take whatever number you got and then divide it by 1,000. 10 to the 3, and then you get 5.52. I guess I'll end just kind of, what did I do here? Because the other thing that you're going to run into with, what are these even called? Numbers where you have like the number times 10 to the 24. You know, for whatever reason, you might think that this is just one number, but it's not. It's the same thing as saying, hey, a parenthesis 5.98, get over it, and now another parenthesis 10 to the 24. Kind of two separate numbers that mean kind of one number. But because of this multiplication, you can rearrange them any way you want, and so that's kind of what we do over here. We say this is 10 to the 3, this is 10 to the 24, that's going to be 10 to the 27. And then we just have this 5.98. Downstairs we have 4/3 pi. We're just going to say this is 6.37. But we do, if we consider these two different numbers that we're then cubing, that's going to be 6.37 cubed times 10 to the 6 cubed. So that's what we do here, 6.37 cubed, and then we're going to have 10 to the 6 cubed. That's going to be 10 to the exponent of 6 times 3, that's 10 to the 18. So we're going to have 10 to the 18 multiplied by 10 to the 6, that's going to be 10 to the exponent of 18 plus 6, that's how you do that, and you're going to get 10 to the 24. So right here you'll get 10 to the 24. And again, if you have 10 to the 24 downstairs, this is the same thing as putting 10 to the negative 24 upstairs. And then this is going to be 10 to the 27 minus 24, which is 10 to the 3. Sorry I'm going through this fast. I'm just kind of getting back in the swing of things. And I don't know, I'm just kind of a little bit less patient, and I want to go to bed. But anyway, so we're at least going to do this in less than 10 minutes. And so, hell yeah. So you got 10 to the 3. You have this 6.37 cubed. 4 pi. I brought the 3 upstairs. And all this also just is 5.52. Why I did it this way is because a lot of these first chapter problems, you're going to be working with numbers that are hella big. And it's just fascinating how, like, hey, you can kind of do this to them. And they're like, I don't know, that looks a little bit more manageable. Now I know that my 10s, you know, if this is 10 to the 24, 10 to the 3, you know, it just feels like when you do like this little x right here for your multiplication, it feels like these two numbers are too wrapped up whereas you can't manipulate them any other way. But the second, oh, bummer, camera, we ended, that was more than 10 minutes. But anyway, so what I was saying is the second that you put parentheses around these numbers, hell yeah, you know what I mean? Then you're like, oh, okay, I can do 10 to the 24 times 10 to the 3. That's 10 to the 27. And that kind of changed my world because what they call this, a scientific number? I don't even know what they call a number where you do it like this. But it's just fascinating. Every once in a while, I'll just take a number like this and then just box it in with parentheses. And it makes the multiplication just look so much easier, and I can kind of cancel it with other things. You know what I mean? Especially when just kind of guessing. I could say that this is basically 6 and this is 6, and you know, I mean, you can do a lot. You can do a lot more with canceling. I think the fact that this, you know what I mean? Because if you divided this by this, you know what I mean? Well, it's not obvious that you can just, hey, let's put these two numbers aside, and we got 10 to the 24 divided by 10 to the 18. You know what I mean? So we're going to have 10 to the 6 up top. I think that's less obvious. Okay, so that was a pretty good nugget. And obviously we do long videos, so if you want to see me talk my way through this one, we go through it pretty good though. So hell yeah, that was the fast version. That wasn't very fast, but now the long version. Hell yeah. Alright, hell yeah. So we have physics for scientists and engineers. This is volume 1, and we're going to try to do every problem in the first chapter. This is problem number 2. Now this answer is not in the back of the book. Basically what they just want to know is what's the density of the Earth, and it says using the end papers. So this was from an appendix. It's the area of a sphere, but you know what I mean. So if the end papers say, hey, the Earth has a mass of basically 6 times 10 to the 24 kilograms, and it has a radius of 6 times 10 to the 6 meters. You know what I mean? So, and then we'll get into that in a second. There's a lot of different ways I want to go about this problem. The first is what I call the units are the equation. So what is density? You know, typically you have two different types. You have mass density and you have weight density. So water, people say, hey, water has a density of 1. Well, like 1 what? And this is probably where you're going to use metric units because it's like 1 gram per milliliter. You know what I mean? And so 1 liter of water is probably about 32 ounces. You know what I mean? So a liter is approximately 2 pounds of water, let's say. And this says that, and that's going to be 1,000 milliliters, so that's going to equal 1,000 grams. And if we're saying that, hey, this is approximately 2 pounds, then that means that 1 pound is approximately, 500 grams. And so cool, you know what I mean? So we have something that's fairly representative. Now that's not true because 1 pound is only like 454 grams. I have no idea. It's something closer to that. So if you had a liter, you would have 1,000 grams, and you would have more than 2 pounds. Oh yeah, that kind of stumped me for 1,000 grams. That's going to be 1 kilogram. So obviously that's 2.2 pounds, and that's kind of what you'll find. So yeah, so I guess a liter it's not 2 pounds of water. It's not 32 ounces. Yeah, a liter is going to be a little bit more, and that 0.2 pounds is how much more it is. Alright, hell yeah. So let's get back to what density is. Sometimes you use this unit of rho for mass density, and this unit of, I think it's gamma. Don't quote me on that, but that's going to be weight density. So weight density would be like pounds. And if it's like soil, you'd do pounds per cubic yard. And then mass density, it's going to be let's see, it's going to be mass, kilogram per, how about meter cubed? Sweet. And so, so let's get back to the fact that the units are the equation for density. So density has units of mass, kilograms, and let's say volume in meters. Obviously those can be different things, but we do have units of mass per volume. But even this, mass per volume, I wouldn't write it like this at first. I would write it in units that you feel most comfortable with. You know what I mean? Maybe it's grams per milliliter. And so you can just write it, you can say that density, rho, is equal to grams per milliliter, and then you can go back and be like, well, what is a gram? You know, a gram is a mass. So cool, that's going to be a mass right there. And then what's a milliliter? You know what I mean? Is that it has a volume, and so we have a volume. Cool. So this is going to be mass per volume. Alright, so hell yeah. So that's going to be the definition of a density. And I think this is going to be helpful. You know, I always say it's going to be helpful like when I learn, you know, about electricity. Because, yeah, I just think electricity is interesting where you have, like, voltage, you have current, you have amps, you know what I mean? And how are they all related? I have no idea. You know, you have resistance. Honestly, don't know how everything is related. You know what I mean? I think I remember some equations, like, no, I can't even spout them off. Anyway, so mass and volume is going to help us figure out the density of the Earth, because now if we want to say, hey, what's the density of the Earth? Well, we can say, hey, what's the mass of the Earth? And then what's the volume of the Earth? Okay, sweet. So one, and this actually might not be the first way to go about it, but let's figure it out. Like, obviously, for the problem, it's pretty simple. We're just going to type in, we're just going to input that the mass is 5.98. So I guess let's just do that. I have a real tendency to actually just go for the problem, because I want to spend time learning other things. But we do have, we just want to make sure our units are right. So we have kilograms. And then the volume of the Earth, well, we need an equation for volume. So volume is 4/3 pi r cubed. So we're going to write volume of the Earth is going to be 4/3 pi r cubed. Now let's take a pause right here, because I didn't have to look this one up. I thought it was like, you know, is the volume of a sphere, isn't that like, you know, is it 4 pi r cubed, or is it, you know, 4/3? I just didn't, you know, quite know. So here is one way that you can kind of guess is, let's take a sphere with a diameter. We're going to take a sphere and then box it in. And this is a good approach. And we're going to say, hey, this sphere has a diameter of 1. And so what would be the volume of this sphere? It would be, let's see, 1 by 1 by 1. Well, isn't that just a volume of 1? So if this was 1 meter, it would have a volume of 1 meter cubed. Now, what did we do to the diameter here? We basically said the volume is the diameter cubed. And then, you know, you could also write this as the volume is going to be some constant, you know what I mean, out front, times the diameter cubed. And guess what? This constant is just going to be 1. Now, we know that's not the case. But that gets us fairly close. Now the other thing that I'm going to estimate is, do I think all the vacant space, like, is all that vacant space equal to the actual sphere, or do I think it's going to be less? Well, I guess the question is, yes, of course I know the volume of this cube is going to be 1 meter cubed, but do I think this sphere is going to be well, let's just guess that the sphere is just going to be 1/2 a meter cubed. Now my question is, do I believe that the sphere is going to be bigger than that or smaller than that? If I had to guess on either side, I would guess that it's going to be a little bit bigger. You know what I mean? I would guess it's going to be like 0.6. If this is 0.5 meters cubed, I'm just going to guess like 0.6. Now, do I think it's 0.7? I don't know. You know what I mean? Maybe. You know what I mean? So I think it's going to be between 0.6 to 0.7 meters cubed, and then we overestimated this. So then our K value on this, our volume of this sphere, is going to be like 0.6 d cubed, or the volume is going to be 0.7 d cubed. Now, and I think this is still kind of a cool way to go about it. Now, we want the volume of a sphere in terms of the radius. So what we're going to do is we're like, well, if the diameter is 1, we'll check this out. The radius is 0.5. And then so if the radius was 0.5, we would still need to figure out the length of one of those, and that's going to be 2 times the radius. And then we would have to take this length times that length times that length. So we would have to take this cubed. When you cube this, you're going to cube the 2, and then you're going to cube the radius. So we would have 2 cubed, that's going to be 9, and we're going to have 9r cubed. And going back to that, that's going to be the, I'm trying not to stutter so much, so I'm going to catch myself while I do that, just because I can always take more pauses. We have all the time in the world, hopefully. And cool, so that's going to be the volume of this, you know, very simple cube, 9r cubed. But we think the actual sphere is going to be about 60 to 70% of that. You know what I mean? Cool. So we're going to take 9 times 0.6. And how would I do that? Just, see, I stuttered. It's all right. So 9 times 60%, that's going to be 9 times 0.6. Well, let's just do, I don't know what 9 times 0.6 is, but I do know what 9 times 6 is. It's going to be 54. 9 times 7 is 63, and then so times the point is going to be 5.4 and 6.3. So cool. So now we know that the volume of the sphere might be 5.4 r cubed, or the volume of the sphere might be 6.3 r cubed. And maybe I've made a mistake anyway. I'm trying to think if I've made any sort of oh, yeah, no, duh. No, I'm sorry, I apologize. I feel like I've already made a mistake, just because in the first situation, I made the diameter 1. And then we figured out, if the diameter was 1, then our area was 1, and this value had to be 1. You know what I mean? Because 1 cubed is just going to give you a multiple of 1 times what it... So, yeah. So I messed up, and that's alright. That's why we kind of play around with this stuff. Make long videos. For this one, I don't know, we'll probably do a short video at the beginning, but I find this interesting. So we're still going to say, hey, this is 1 meter right there, and that's 1 meter. Instead of 0.5, yeah, so this was kind of a mistake, I think, because now we're going to come over here and we're going to say what's the volume, like definitely the volume of this easily is going to be 2 times 2 times 2, that's going to be 2 cubed, that's going to be 2 times 2 is 4 times 2 is 8. So we have, this is going to have a volume of 8 meters cubed. And if we said the radius was 1, we would have to take one of the sides, so that'd be 2 times the radius of 1, and then we would cube it. And that's where we get that. So we would get 8r cubed. Yeah, am I just freaking out? You know what I mean? I'm just making mistakes all over. We're trying to just get back into... I haven't made videos in a while. But yeah, 2 cubed is not 9. You know what I mean? I don't even know what the hell I'm doing. So we can just totally scribble out all that. But we'll get back to this in a second. So we get... so we do get... the volume is 8r cubed. When the radius is 1, cool. We get a volume of 8. So that works out. Yep. Now, okay, yeah, but that's a huge overestimate, you know what I mean? Because if we have this sphere inside of that cube, the cube, the sphere is much less volume. So, you know, we can just guess that it's going to be, hey, maybe it's 4, maybe it's 5, you know what I mean? So I think the volume of the sphere is very close to half. So I'm just going to say it's 4r cubed. So now, now we know that the volume of a sphere is 4r cubed. That's a fairly accurate guess. And even right here, you might be like, well, is that the volume of a sphere? Volume of a sphere is just 4r cubed. And doesn't that look drastically different than 4/3 pi r cubed? Well, yeah, this is where using pi messes you up. I mean, this says 4/3 pi r cubed. Well, pi, you know what I mean, for all intents and purposes, is just very close to 3. Call it 3, so we're going to have 4 times 3 divided by 3, r cubed. Cool, the 3's cancel, and literally the volume of a sphere is just 4r cubed. And so I love doing this type of stuff because it'll help you guess at other things. It'll help you make better estimates. You know what I mean? There's no reason to do this, but this is the best place to do stuff like this because you already know what the equation is. But like I said, let's say I didn't want to look this up and I wasn't able to look that the volume of the sphere was 4/3 pi r cubed. But I just wanted to double check that I didn't say that the volume of a sphere was 4 pi r cubed, because that would be off by a factor of, that would be, 3 times bigger volume, because you'd have to take, if that was the volume that you got, whatever number, you got to divide by 3, and then you'd actually get the volume of the sphere. Okay, so hell yeah, so that's, and did we show that, yes, if pi is essentially 3, the 3's cancel and you get 4r cubed. So our estimate that when you throw a sphere inside a cube, it's fairly close. So let's figure out when you do that. When you do throw a sphere inside a cube, the actual equation is going to be 4/3 pi, and then we're going to say r cubed, but we're going to have a radius of 1. You know, so that's 1. And so the actual volume is, and we thought, I don't even know what we thought. Oh, we thought if it was half, if it was half 8r cubed, you know what I mean? Because the actual cube itself is 8 meters cubed. And if this was 4, if these two did cancel, it would be half. But these don't cancel. This one is bigger. So the sphere is greater than half. So at least we know that. The sphere is bigger than 4 meters cubed. It's going to be like 4 point something. You know, I don't think it's going to be 5 meters cubed, but we can find that out right now. So we're going to go 4 times pi divided by 3. Yeah, it's only 4.1. It's 4.19. You know what I mean? So, but yeah, I like doing this. There's really no reason to do this for this problem, so I'll definitely put the fast answer at the beginning. But I do like going over that type of stuff. Alright, let's see. When we said this was a cube of 1 meter by 1 meter by 1 meter, and the diameter, you know, was 1 meter, we said the volume was going to be 1. So this has a volume of 1 meter cubed. The sphere we thought had a volume of 0.5 meters cubed, and we wouldn't be too far off. You know what I mean? So let's go back to here, and that would be the same as saying the radius is 0.5. So we're going to go 0.5 cubed times pi times 4 divided by 3 times 4 divided by 3. And yes, we get 0.52. So we get fairly close there. Alright, hell yeah. So I'm glad I went over that, but now let's take a step back, because this problem let's go back to Newton, because Newton was able to do quite a bit with his equations just by guessing the density. He didn't know the density of the Earth, but he guessed it, and then he could guess the mass. So the first thing, and I had to look this up, because so let's say you do have a problem. It says, let's just read this. Use the information on the end papers to calculate the average density. We know that's mass. So what's the mass of the Earth? You know what I mean? That's a great question. Let's just say no one knows. And then, but the density also has to do with the volume of the Earth. You know what I mean? What the hell's the volume of the Earth? Well, we do know what the volume of a sphere is, and maybe you could figure that out empirically or whatever. But how do we figure out what the volume of a sphere is? Well, we boxed it in and figured out what the diameter is. Well, how do we know what the diameter of the Earth is? You know what I mean? How do you know what the size of the Earth is? So that's where I even went online and just well, how did they actually know? Because one of the, in 2024, one way that I always kind of have a grasp of what's the circumference of the Earth. I know that on Earth there's going to be 24 time zones. You know what I mean? And if you live in a fairly big country, I live in America. We got 4 of them. You know what I mean? And maybe 5 or 6 if you compare Alaska and Hawaii. So that's a pretty good represent. But I live in a state where you can drive from one time zone to the other time zone, and it's about 700 miles, 700, 800. And then I just know that at the equator, that's 1,000 miles. So I have this in my head that a time zone is just really close to 1,000 miles, and there's 24 of them. So right off the bat, I know the circumference of the Earth is 24,000 miles. Now that's using common things that we definitely take for granted, knowing that we already have these methods of measurement, and we already know, you would have to trust that that's a time zone, you know what I mean? So it's just fascinating. I had to look up what was the first way to actually figure out the size of the Earth. And so let's go over this, because it was, I had to kind of figure this out myself a little bit, just to make sure they did it right. So you do have, let's say you do have the Earth, and it was in Egypt where, let's say, and what was it? Was it? I forget the 2 locations. One was, I would just assume that this one was where high noon cast no shadow. Is the whole hey, at the summer solstice on this day, there was no shadow cast into the well. You know what I mean? So you could have a vertical plumb bob, so you could do that experiment. A vertical stick, you could make sure your stick is vertical because you've measured it with the plumb bob. I mean, we're talking, I think this was set, man, I'm going to get my dates wrong. You can look them up yourself. But then they knew the distance north. But that's the thing, is that let's say you just went east and west. Well, the Earth is kind of spinning this way, so the sun would still be totally vertical overhead. Any stick wouldn't cast a shadow on the summer solstice, blah, blah, blah. So that was the interesting thing about this, is that you would have to collaborate with a couple people, one being in a town over here, and the other, it was said that, and I don't even know the scientist or the observer or the physicist, but it was the tale. A lot of these are just kind of tale-ish, compared to how they actually did it, because you could repeat it, but I don't know. Like they said, yeah, on this day, they knew that there was no shadow cast in a well, so you just knew that, Now you can go to this other location up north, or you could go south, it doesn't really matter, and then also have a vertical stick, and then just know it's that same day of the year that the other town cast no shadow, and you can just wait. You could wait all day for the most minimal shadow. So let's say you are waiting, And so here's the sun rays coming down, and you do have a shadow right here, but hey, maybe the sun's moving across the sky, and so then it creates a shadow like right here, but it never goes fully vertical, like, however the sun moves across, it doesn't get totally vertical, it just comes here and then goes sets. So cool, you're going to measure that. That's going to be like on the summer solstice, that's the most vertical the sun's going to get. The rays are totally, and you can look this diagram up, but I get that. That's the cool thing about this experiment is, like, I could try to mimic it. It would be kind of difficult, but I don't think it would be. And I don't even think you need the summer solstice. I think you just need any, like, even what I was thinking, if I was ever to drive north, anytime I was driving north or driving south, the day before a road trip, I could just, make a vertical stick and leave a camera on it and just make sure to see what the angle, what the distance, what the minimum shadow, because if it's casting a big shadow and then near high noon it's casting this shadow, cool, then go to the other location, whether it's south or north, doesn't matter, and then see if that shadow's different. If it's less, maybe I'm going south and going closer to the equator and it's getting to be less, then I know the distance between those 2 points, and then I know this one is actually pretty easy. Alright, this one was pretty easy for me to, understand, even though, I don't know, probably the geometry is just, but basically the difference between those angles is going to be the representative slice. So if I do draw a globe, and I was here, and then I went south, and then this is the change in angle between these two shadows. This is going to be the angle, like whatever the change in angle right there, we're just going to call that theta. That's your theta. And if I know the distance of how far I traveled south, well, cool. And let's say this distance was like 1 degree. Well, whatever this distance traveled north to south is going to be times 360 of that. And obviously, I think driving 1 degree is probably, if there's 24,000 miles, let's even see if that even makes sense. 24,000 miles divided by 360. Whoa. Divide. I guess that's just 66 miles. Oh, that's fascinating. I'm glad I did that. 24,000 divided by 360 degrees. Every 66 miles is 1 degree. Whoa, so every 66.6 miles times 360, that's going to give you 24,000. Am I doing this right? I think so. Who knew that, 60 miles doesn't seem like much. And it would take you 360 days to get around the Earth. So 1 year. If you only move 60 miles, it would take that. I guess it's fairly easy to drive across country, which is a big representative of the Earth sometimes. But anyway, all right, that was fascinating to me. But then the other ones were just like, well, what's the mass of the Earth? Well, holy hell, that's much later in the discovery. Now Newton was able to figure out this equation. The force of gravity is going to be a gravitational constant, whatever the mass, like let's say mass of the Earth, mass of the Sun, and then the radius, the astronomical unit basically between those two distances. But yeah, the distances between two masses times the gravitational constant, and yeah, so he was able to use this universal gravitation to, he knew, yeah, he was using this equation. He came up with the universal gravitation, but he just guessed what the mass of the Earth was. And he must have maybe guessed what the mass of the Sun was, and maybe guessed what the mass of other planets were as well. But how do you guess the mass of the Earth? I guess that's where we're going, and then we'll kind of finish with the right answer. So, I don't know. I think you have to you know what I mean, have the Earth in your mind, and let's just say the mass is only what's solid. You know what I mean? So we're talking water, rocks, and whatever's on the inside. Cool. So what do we know about the water? The water has a density of 1. Now, here's a good question. What does rock have? I definitely took a soil science class, and you'd always be like, well, rock is 2.65. And like I just remembered that, because if you look it up on Google, rock is anywhere between, common rock is 2.6 to 2.7 grams per milliliter, you know what I mean? And that's density of rock. So cool. So the Earth has water. It also has rock, 2.65. But what else does it have? Well, we know it has an iron core. And iron has a density, this is a good one to remember, it's 7 I would say 7.7, is it 7.75? You know what I mean? Is it 7.8? You know, it's pretty close. I think this is actually really accurate, 7.75, but 7.8. Yeah, 7.7. But anyway, let's just say 7.8. So cool. Iron has a density of 7.8. So let's say the Earth, and then who knows, maybe there's like a neutron star in the center of the Earth. I have no idea. Maybe when you actually compress iron, it actually gets heavier and you get a higher density in the middle because of all the pressure. Who knows? But actually, I don't think so. Even liquid, I mean, it definitely turns liquid because of all the pressure. But I don't think it actually, I'll have to look that one up. What's the density, what's the highest density in the center of the Earth? Because this is fascinating. A star has an average density of just 1.4. The sun has an average density of 1.4. So I'm going to click off the camera because the inside of the sun has a density of 150 times water, and most stars, you know, and the density of the sun is 1.4, but on average, if you want to take all the stars in the known universe, you can just, you know, basically on average say they have a density of 1. And let's see. And that's fairly useful because we kind of know what the mass, like you can figure out what the mass of all those stars in the universe are by figuring out how many numbers there. But anyway, I'm actually going to go look up what the max density, you know, just from a Google perspective, what's the max density of the Earth. But basically what we're getting at is like, well, wouldn't the density of the Earth be between 1 and 7, you know, 1 and 8? You know, it's not going to be 9. Well, unless for whatever reason, when you compress all that iron, it like, you know, triples in density. I have no idea. But that aside, because I don't think it actually increases too much. You know what I mean? A star, I get that. It's a lot of mass, and it's, you know what I mean? It's a lot of mass that's densely packed. Where the Earth isn't that large, you know, from that perspective, sure, it's a lot of pressure that it turns iron into molten iron because of all that pressure, you get heat. But right here, you can just choose. What do you think? The density of the Earth is 5 and 6? I think it's just between 5 and 6. I don't think it's as low as 4, but it might be. You know what I mean? So I'm guessing between 4 to 6. Those are my guesses for the density of the Earth. And this could be what Einstein did. I mean, obviously, if I was a physicist, I wouldn't know that the center of the Earth is iron. Even molten lava only has a density of like 2, like 2.2, I think, because it's a lot of lava is basalt. You know what I mean? So it's not, you're not just having molten iron like come to the surface. So there might be, it might be very difficult for early physicists to know that the center of the Earth is different than the density of like common rock. And I don't know, it's just like, yeah, I'm going to look this up because it's just fascinating. Planet's pretty big, maybe the density of its core is just denser, and I mean, is it a density of 20? You know what I mean? Some of the densest metals are pretty close to, you know, up here, 20. But anyway, so yeah, let's look that up, and I'll catch you on the flip side. Alright, hell yeah. So, I just looked up online that the density of the center of the Earth can get up to the density of 13. And the most dense metals are over 20. Gold's pretty close to 20, if not, is it 19.9 or something like that? Or is it over 20? I'm not quite sure, but the densest metals go from 20 to 22. You know, you got gold, you got uranium, you have platinum, iridium, and then osmium. That's going to be your densest. Okay, sweet. So I'm going to end the video here because I'm going to do this all in one go. Like, obviously, you're just going to find the density is mass divided by volume. That volume is 4/3 pi r cubed. We do know that the radius is in meters. We'll have the mass in kilograms, and then we'll have a density of kilograms per meter cubed. Now, is that what we want? Now, milliliter, is that actually a volume? I got to think about this. Holy hell! Like a milliliter. Yeah. Is that I have to pause the video. Oh, no, we're good. Yeah. So a milliliter is 1 centimeter cubed. So that's kind of the definition of a milliliter. Yeah, that's interesting. So I have no idea what the usefulness of milliliters is in the metric system compared to a volume. Is this just liquid volume? You know what I mean? A milliliter. Oh, that's fascinating. Like, yeah, why wouldn't you just say centimeters cubed? Maybe because it just sounds better. Oh, that's messing with me. Even the metric system's pretty tight, but man, that's kind of that is messing with me. All right, so we actually, man, I should let's just do this once, and we can always do the fast version at the end. Because what we're going to have to do is, instead of kilograms, we're going to have to take kilograms to grams. You know what I mean? So there's going to be 1,000 grams equals 1 kilogram. So we'll have to figure that out. And then meters. How many centimeters are in a meter? Well, I do know that there's 10 to the 6 centimeters cubed in 1 meter, and we can talk about that. So, yeah, let's just kind of go at a nice slow pace. Alright, hell yeah. So let's do this. So we're going to do the density of the Earth is the mass of the Earth divided by the volume of the Earth, which is the mass of the Earth divided by 4/3 pi radius of the Earth cubed. Cool. So from our literature, the mass of the Earth is 5.98 times 10 to the 24. It's a good one to memorize. It's 6 times 10 to the 24. That gets you pretty close. You can probably memorize 5.98. That's pretty good. Or pretty simple to memorize because it's only 0.02 off. And then we're going to go 4 divided by 3 pi. Radius is going to be kind of 6 times 10 to the 6. This one's a little bit harder to memorize because it's, 6.37? But even, you get used to writing 6.37, so you can even memorize that at some point. I guess I didn't. But this is going to be in meters, and then we're going to cube it. Now, let's do all of our conversions just right now. So we want to get to grams per milliliter, which is the same thing as grams per centimeters cubed. So how I convert, especially when you got like meters, this is going to be meters cubed. And again, if you take a look at this, you're cubing this number right here, and then you're cubing the units as well to get a number in meters cubed. And then even though that you have this in scientific notation, it's the same thing as cubing this number, and then also cubing 10 to the 6. You know what I mean? So, so yeah, you could say this 6.37 cubed times 10 to the 6. You'd have to do this cubed, and then meters cubed. And if you got kind of clever, you could be like, well, this is 6.37 cubed times 10 to the, well, if we're doing 10 to the 6 cubed, then that's going to be 6 times 3. So this is 10 to the 18, and then you would have meters cubed. So that's also the same. Okay, how do we convert it to centimeters cubed? Well, what we would do is we would recognize that we'll have meters cubed upstairs, so we would have to have, well, first thing I'd do is just do this. Let's just do 1 meter downstairs, and then what's that in centimeters? Maybe I don't know, but I do know that 1 millimeter is 1,000, no, 1 meter is 1,000 millimeters. Nice. And then I can go, let's say 10 millimeters is 1 centimeter. So maybe, I don't know how many centimeters are in a meter, but now I would, because there's going to be 100 of them. But maybe I didn't know that. So I would do it that way. I would say, hey, I know that 1,000 millimeters is 1 meter. Meters is upstairs over here, but it is meters to the cube. But still, I just pretend that it's, forget the meters to the cubed or squared or whatever for the time being, and just know that the factor label method, you'll have to, if meters is upstairs here, it's got to be downstairs here. And now to make this work out, you have to cube this and then cube this. Because now we're going to have meters cubed, and that's going to cancel these meters cubed. Now this is the same thing as saying 1,000 cubed millimeters cubed. See how we're taking this cubed and we're applying it to this number, this unit, this number, and this unit. This number is just 1, so we're just going to have 1 cubed. That's just 1. But then we have meters cubed. So what's 1,000 cubed? Maybe I don't know that, but that's 10 to the 3. That's 1,000, and then we're going to cube it. And then so that's going to be 10 to the 3. That's going to be 10 to the 3 times 3. You know what I mean? So that's going to be 10 to the 9. Cool. So now we're going to have 10 to the 9 millimeters cubed divided by 1 meter cubed. And then over here, same process. We're going to have 1 cubed, centimeters cubed, 10 cubed, millimeters cubed. And I don't know why I'm just assuming that everyone knows all this, and I'm just hand-waving that this is an easy problem, but no, I always forget. Yeah, this factor label method, I've done it in other videos, but it's just really good to do it this way. And again, what I'm doing is I'm identifying that I need to convert meters to maybe millimeters, then millimeters to centimeters, or I'm converting meters to what I need, and that's going to be centimeters in the end. But I do need it cubed, and so I do this process of understanding how I'm getting that. Okay, so here I'm going to have 1 centimeter cubed. This is 10 to the 3. So I'm just going to write that as 10 to the 3 millimeters cubed. So these millimeters will cancel. This 10 to the 9 divided by 10 to the ones, kind of are irrelevant. But 10 to the 9 divided by 10 to the 3. That's the same thing. This is 1 divided by 10 to the 3. So that's the same thing as 10 to the 9 times 10 to the negative 3, if that's a good way for you to know it. Also, that's 10 to the 9 minus 3. And that's going to be 10 to the 6. So sweet. After all that, we basically get this whole thing right here is equivalent to saying 1 meter cubed is 10 to the 6 centimeters cubed. You know what I mean? So that is the conversion factor that we've shown. And so how do we is that what this says? Yes, we're going to have 10 to the 6 upstairs, and we got centimeters cubed. Downstairs, we're going to have 1 meter cubed. 1 meter cubed. Yep, so everything else cancels. You know what I mean? And so there's our conversion factor. Hell yeah. And cool. And then for this kilograms, we're going to have, we need kilograms downstairs, so we'll have 1 kilogram downstairs, and then we're going to have 1,000 grams upstairs, and then so that's what we need to do. So all in all, we need to take this number, or after we cube the radius, we have to multiply by 10 to the 6, and then multiply by 10 to the 3. So essentially, we'll have to multiply by 10 to the 9. So let's go ahead and do that. Alright, hell yeah. So yeah, let's go ahead and do that. So we're going to go 5.98 times 10 to the 24, divided by 4, well, how do I want to do this? Yeah, I guess, divided by 4/3, divided by pi, divided by 6.37 times 10 to the 6, cubed. So I didn't want to just do like an all divided by, I don't know, you know what I mean? I'm not going to go over that, but you know, figure it out, put it in your calculator to make sure you get the right answer. And so we're going to do that, and then, oh, hell no. I feel like this isn't going to work at all. Oh, where did we make a mistake? Man, this is bumming me out. 6.37 times 10 to the 6. This is 5.98 times 10 to the 24. Holy Toledo. Oh, you know what? Check this out. After all that, yeah, you know how we had to multiply by 10 to the 6? Yeah, all that stuff's downstairs. My bad. You know, that was a huge error on me. So this meters cubed is downstairs. You know what I mean? So when we do our conversion factor, we're going to have 10 to the 6 downstairs that we multiply by, and then we're going to have 10 to the 3 upstairs. So that's the same thing is at the end, just dividing by 10 to the 3. Wow, we're getting really sloppy on this, but at least we're catching our mistakes. So if this is the answer we get, we divide by 10 to the 3, and we get a density of the Earth of 5.52. Alright, sweet. So the factor label method is probably the part that I should have spent, well, I think I spent enough time on it, I just made an error. And I definitely like making errors because it's kind of fun to see where I make them. But yeah, that's also the bummer about these problems, and that's why these first chapter physics problems are useful, because you have to almost use numbers that are nonsensical. 10 to the 24, like honestly, if you take all the mass in kilograms of the entire universe, it's not more than like 10 to the 120. There's not more than 10 to 120, even individual like protons or neutrons. I don't even think there's that many protons and neutrons in the universe, let alone kilograms. You know what I mean? So yeah, so just even using 10 to the 24 or 6 times 10 to the 6 and then cubing it, which gives you a number like 10 to the 18, 10 to the 19 maybe. So yeah, it's just it's almost nonsensical. You know what I mean? So that's going to be the hardest thing, where it's just like, yeah, and then just after all that, heck yeah, you get something that's familiar, but you can easily mess up. So that's why just kind of guessing, hey, the density of the Earth is going to be between 4 and 6. We did a pretty good job there, but we weren't quite sure because the density of the Earth in the middle can be pretty dense. So that was pretty cool, but sweet. So the average density is 5.52. I'd be really impressed if I could ever find out what Newton's guess was. You know what I mean? Like, and maybe kind of how he developed that guess. You know what I mean? But like, what did he guess? Did he guess 4? Did he guess 5? Did he guess 6? But hell yeah. And this answer is not in the back of the book, so 5.52. I'm going to do a little quick version. But thanks for joining me on this one, and hell yeah.